Good morning, everyone. Thank you for joining us. I'm very happy to introduce Christian Rosendal from University of Maryland, and he will be speaking on the relation of coarse embeddability between Banach spaces. Christian?
Yeah, okay. Thanks for the invitation, and it's nice to see you all again. Okay, so I'll give you a board talk here. All right, so what is this about? Well, it's about understanding a somewhat specific problem around coarse embeddability, namely what it means for one Banach space to coarsely embed into another. And what I'm going to say, of course, when one looks at coarse embeddability, one often considers metric spaces instead, where these things they're really defined in that category, or maybe even beyond that. But what I'm going to do is specific about Banach spaces, because some of the techniques are really specific to Banach spaces. Okay, so let me start with the motivating question. So I thought for a long time that this was posed by Calton, but I think that's perhaps more my reading of Calton's papers than Calton actually being explicit about it. But it's certainly indicated in some of Calton's last papers on the nonlinear geometry of Banach spaces. So the lack of understanding of these specific things. Okay, so the question is, if you have two Banach spaces, X and E, I'll always use X as my domain and E as my range, so I can keep track of, I can use X's and Y's as variables of X. So if I have two such Banach spaces, and maybe you want to restrict to separable Banach spaces, that's really the main case I'm interested in, but whatever, I haven't seen any differences between the separable and non-separable category. So if I have two such Banach spaces, are the following equivalent. Okay, so there's A that X embeds into E uniformly. Okay, so there's a homeomorphism between X and some non-linear subspace of E, so just some subsets, and B, whether so X embeds coarsely into E. Okay, so is it the case that for all Banach spaces X and E, X embeds uniformly into E if and only if it embeds coarsely? Okay, so before I start defining these things precisely, let me just note that, of course, uniform embeddings has to do with the small scale geometry of the Banach spaces X and E. Okay, this is something that's X can maybe completely collapse into a bounded subset of E, whereas on the other hand, the coarse embeddings has to do with large scale questions of X and E. So coarse embeddings don't even have to be continuous or anything. So this is really not about the topology, but the large scale geometry. Okay, so that's the motivating question, whether these two notions are the same. And I'll give you some answers here and indicate that really the uniform embeddings are somewhat stronger than coarse embeddings, at least on the face of it. Okay, so So note that I'm not asking whether every uniform embedding is a coarse embedding or that every coarse embedding is a uniform embedding. This is not the question. The question is, if there is a uniform embedding, is there then some other coarse embedding and vice versa? Okay. So a few comments. Some observations. Okay, so the first thing is that if we look at instead of embeddings, we look at equivalences, then we see that every uniform homeomorphism is automatically a coarse equivalence. Okay, so uniform isomorphisms are automatically isomorphisms in the coarse category. Okay, so that indicates that the uniform category somehow has more information, and conversely, Kelton he proved that there are coarsely equivalent spaces that are not uniformly equivalent, are uniformly homeomorphic. So that's, again, this is an example that shows that the uniform category is really sort of stronger than the coarse category. But this question that I'm interested is about embeddings, okay, and ultimately with applications to metric geometry. Okay, so now comes the main culprits here in the talk. These are the so-called functional coefficients. Okay, so these are the some functional coefficients associated with every map. Okay, so suppose I have a map, okay, between two Banach spaces. So henceforth, X and E will always be Banach spaces, and phi is some map. So it's in general, discontinuous map. It's in general non-linear. Okay, so there's no algebraic properties preserved. It's just some function from X to E. Okay, and so maybe I'll just assume also that X is not just the trivial space. So it has a dimension at least 1, just to avoid some trivialities. Okay, and so then associated with this, I can define two functional moduli, two functional coefficients, okay, that I'll denote omega of phi. Okay, what is this? So this is, well, it has to do with the modulus of uniform continuity, even though phi may not be uniformly continuous. So what I do is I look at the infimum for t greater than 0, and then I take the supremum over all pairs x, y, whose distance is at most t, and then I take phi of x minus phi of y in distance here. So I'm taking the supremum here. So I'm taking the infimum over a supremum. Okay, so this is the question of if I bound my initial distance between x and y, how far can x and y go from each other? Okay, so this is called the expansion coefficient. Okay, and then I will also have a compression coefficient, which is defined in a similar way, but sort of dual to this one. So I'll take the supremum, and now rather than insisting that t be positive, I insist that t be finite. So I'm taking finite t, of course, really just take for t positive real, yeah, but write it out so it's suggestive. And then I'll take the infimum of now for x and y that are separated at least by t, and then I'll take phi of x minus phi of y. Okay, so this is the compression. Coefficient. All right. Okay, so these are two numbers that you can associate with every map. Okay, so these are two numbers. Well, numbers in a generalized sense. Okay, they can both be 0 and they can be infinity. So omega of phi and kappa of phi, they are in the interval from 0 to infinity. Okay, infinity included. Okay, so let's see here. There are sort of 4 cases of interest. So let's go through them individually. Okay, so what does it mean for the function phi to be uniformly continuous? And uniform continuity, let's remember that means that for every epsilon, I can find a delta. Okay, so if things start delta apart or delta close, then they are also epsilon close in the range. Okay, so uniform continuity is simply the statement that omega of phi is equal to 0. Okay, so omega of phi being equal to 0 means that, well, for every positive real, I can find some t so that if things start at most t apart, then they will become, then that distance in the range is also like as close as I want it. Okay, so this is phi is uniformly continuous. Okay, so that case we know. Now, if I weaken this condition, okay, of being uniformly continuous, and instead I just ask that, well, the supremum here at least shouldn't be infinite. Okay, what is this? This means that there is some t, so that if x and y are within t of each other, then their images are within a uniform bound of each other. Okay, this is the same as being Lipschitz for large distances. So phi is Lipschitz for large distances. Okay, and I'll just write that down. Okay, so that is so you have some constant k, so that phi of x minus phi of y in norm is at most k times the norm of x minus y plus k. Okay, for some uniform some k a and all xy. Okay, so Lipschitz for large distances is just this condition, and this of course uses that I'm at least working in a Banach space as some type of geodesic metric space X. All right, so these conditions are well known. Let's, on the other hand, now focus on what happens with this coefficient kappa of phi, which is the compression coefficient. So rather than asking, well, how far can two close points become, I'm asking, well, if I have 2 points that are far apart, how close can I bring them to each other in the range? And that's what kappa measures. So here I have the third condition. The first one is that, well, the strongest is that kappa of phi is infinite. Okay, this is well, denote this by saying that phi is expanding. Okay, so that is we'll write it out. So for all delta, okay, finite really, there exists capital delta also finite, so that if x and y are delta, capital delta apart, then their images is at least delta apart. So doesn't matter how far I want phi of x and phi of y from each other. Okay, I have some bound so that if they start capital delta apart, then they become small delta apart in the image. And then finally, the weaker condition is that, well, at least kappa phi is positive. Okay, this is denoted by saying that phi is uncollapsed. Okay, it doesn't completely trivialize. So what does that mean? This means that now I just have 2 delta here, again finite, so that if x, okay, they should be positive. It's rather the other way around. Positive. So if x and y start capital delta apart, then they're images. Yeah. Small delta apart. So that's just some tiny delta, okay, small delta, so that and a humongous large capital delta, so that if things start at least capital delta apart, well, then the distance in the image will at least be that big. Okay, it's not completely collapsing all distances. Okay, so these are the 4 conditions that you look at. Okay, when omega is 0, omega is finite, kappa is infinite, or kappa is at least positive. Okay, so those are the 4 conditions that are sort of interesting. Now, already with this, I can now express when phi is a coarse embedding in terms of these coefficients. So then I can put it as a definition. Okay, so phi is a coarse embedding if, okay, so by definition, if and only if it's Lipschitz for large distances. Okay, so that was condition 2. So if phi is Lipschitz for large distances, and uncollapsed. So again, so that okay, let me write it out. So kappa of phi, if I take kappa of phi over omega of phi, okay, what is that? That is, sorry, this was, no, sorry, it's not uncollapsed, it's expanding. That's what I wanted to say. Okay, so it's Lipschitz for large distances and it's expanding. Okay, so that means that kappa of phi has to be infinite, omega of phi has to be finite. Okay, so if I'm taking infinite over a finite number, well, of course, I should get infinite. So if I have a coarse embedding, this ratio between kappa of phi and omega of phi is infinite. Okay, so it looks like that's an important number of the associated with the map. So let me give that a name. Okay, so the separation ratio of a map, abstract map between two Banach spaces is this number that I'll denote R of phi, which is kappa of phi divided by omega of phi. Okay, and of course, well, there are some cases, as we can see, I have sometimes to divide an infinity by 0, etc. So let me just have the conventions in place. I'll say that a divided by infinity is the same as 0 divided by a, and that's always 0 for all a. Doesn't matter what a is. Okay, and on the other hand, I'll say a divided by 0 equals infinity divided by a equals infinity divided by 0 for a in the open interval. So if I have some positive, strictly positive number divided by 0, or infinity divided by 0, that's infinity. Infinity divided by something finite is again infinity, and on the cases I get the 0. Okay, so that's the separation ratio, okay, of a map. So maybe I should just say initially what the separation ratio is. So let me give an observation here, okay, to see how weak the separation ratio as a number is. Okay, so I'll note that if I have a constant k, then the separation ratio of a map is strictly greater than k, if and only if, well, I should be able to find some numbers, lambda, capital lambda, lowercase lambda, delta, delta, all positive, okay, such that, well, okay, what do I want? I want that delta over lambda is greater than k. And I want that, well, if x minus y is at most capital lambda apart, then the images at most lambda apart. And if they start out delta apart, then the images are at least lowercase delta apart. Okay, so the separation ratio of a map, okay, this is a single number associated with the function. Okay, so I'm not having some functional moduli that expresses something about the compression and the expansion moduli, which are really functions from the reals to the reals. No, I'm boiling it down to just a single real number that expresses something about the map. Okay, that it doesn't.
Let me ask you.
Yeah.
Do you really mean that infinity over infinity is 0?
Yes, I don't. Okay, I'm just putting it equal to 0 because that's a bad case for me.
Okay.
All right, let's see here. Because these 4 cases are the ones of interest. So if I had infinity over infinity, then I would have a map which is not even Lipschitz for large distances. Okay, so that is not helpful for me. Okay, so I want the only case, if I should have something positive, then I want at least that the map is Lipschitz for large distances.
Okay.
Okay, this is why. So that condition is here. Okay, this condition here, this ensures that the map is Lipschitz for large distances. All right. Other questions so far? Okay, good. So as you can see, this separation ratio, well, okay, that having it greater than k is really a rather weak condition. Okay, it's just something that is about a pair of distances. It doesn't completely collapse a certain distance, and it doesn't completely explode a certain other distance. Okay, and the ratio between this this delta and lambda is what I'm interested in. Okay, so another thing. Okay, so in particular, okay, we see that, well, this separation ratio is infinite. When does that happen? Okay, so I already said here that if I have a coarse embedding, then the separation ratio here, which is given there, it must be infinite. Okay, so okay, so that's one of the options. Okay, so this is that. So if either phi is a coarse embedding, or B, the other case when it's infinite. Okay, so either I had that this was the coarse embedding was infinite over something finite. The other case when I have something positive over 0. So that is when phi is uniformly continuous and uncollapsed. Okay. So uniformly continuous, you certainly know what that means. Uncollapsed, I remind you that this is just that there's some distance that is not completely collapsed to 0. Okay, this condition here, okay, that there are some capital delta, so that things delta apart can't get contracted arbitrarily close to each other. All right, now, so okay, so the next, so in the following, I'm gonna have use a certain assumption on E that will come up again and again. Okay, so this is the first theorem that is sort of a refinement of things that I proved a number of years ago. Okay, so suppose X and E, they are Banach spaces. and such that I assume that E plus E linearly embeds into E. Okay, so there's some embedded. So E, the direct sum of E and E is an isomorphic to some subspace of E, not complemented or anything, just some way or another. Okay, so assume so if there is a uniformly continuous and uncollapsed map from X to E, then there is a map phi from X into E that's simultaneously a uniform and coarse embedding. Okay, so not only, so I start with a thing, okay, with that's uniformly continuous and uncollapsed. Okay, so for example, if I had a uniform embedding of X into E, this is certainly uniformly continuous, and it will also be uncollapsed. Okay, that's uncollapsed is much weaker than the inverse of the function being uniformly continuous. Well, then, in fact, I can both, then not only can I coarsely and uniformly embed the X into E, but I can do it simultaneously by a single map. Okay, so as I said, a uniform embedding is always uncollapsed. So we get that the corollary, so uniform embedding, so if X embeds into E uniformly, this implies that X embeds into E coarsely. Okay. Of course, this is under the mild assumption that E plus E embeds into E. Okay, so I will have that assumption underlying here. Okay, so well, I can sort of live with that assumption in most cases. So largely, this responds to the question of whether uniform embeddings imply coarse embeddings. But of course, it doesn't imply give you the other direction. Okay. Well, except that, see here, if I have a coarse embedding of X into E, okay, well, that coarse embedding will be much more than just uncollapsed. It will be expanding. Okay, so uncollapsed is a very weak assumption here. Okay, but as I said, the coarse embedding need not be uniformly continuous. However, if I can get a coarse embedding that is uniformly continuous, then I can also get a uniform embedding. Okay, so let's write this down. So if there's a uniformly continuous coarse embedding of X into E, then X embeds uniformly into E. So, well, all right. So that looks like you're close to solving the converse direction. You go from a coarse embedding, okay, maybe you smooth it a bit, okay, and then you hope that you can get it to, by modifying sort of it locally, you can make it uniformly continuous. So now you would have the uniformly continuous and coarse embedding, and then you do some other, you appeal to this corollary and says, then I can get another uniform embedding of X into E. Okay. Well, the problem with that is that, so this was considered by Naor, this issue, and he proved that there are separable Banach spaces X and E, and a Lipschitz for large distance map phi going from X to E. Okay, so I can find some map. It's not going to be a coarse embedding, but it's at least a map that's Lipschitz for large distances. So it has the properties going forward that the coarse embedding will have. Okay, such that this map is not close to any uniformly continuous map. So that means that for all uniformly continuous maps C here, I get that these two maps are very far from each other. So the supremum of the distance between phi of X and psi of X is infinite. Okay, so this is some cohomological assumption here, no, consequence here, that this is really a class in a different closeness class than phi. Okay, so you can't just start out with a coarse embedding and then hope to modify it locally to get another uniformly continuous map and then appeal to this corollary. All right, so this is some older considerations here. So that deals with the uniform versus coarse embeddings. Now I want to just consider exclusively coarse embeddings and see how weak the assumption of X embedding coarsely into E really is. Okay, so let me remind you before I let me write it down again. Okay, so in the following again, so assume that E plus E embeds linearly into E. Okay, so I'll just write it like this. Okay, so I'll have E plus E as some subspace of E up to isomorphism. Okay, so from the above, so then we have okay. So I know that, okay, if I have a coarse embedding of X into E, well, okay, that coarse embedding okay, what did it satisfy? It satisfied that the separation ratio was infinity. So every coarse embedding automatically has separation ratio infinity. Okay, now there were two types of maps that satisfied the condition of having infinite separation ratio. There were coarse embeddings. Okay, let me go back to this. Yeah, okay, there were two ways that you could get infinite separation ratio. Either that you are a coarse embedding, or that the map was uniformly continuous and uncollapsed. Okay, and now this theorem, the following theorem says that, well, if I have a map that's uniformly continuous and uncollapsed, well, then I get a coarse embedding. Okay, so both of these assumptions here, okay, so either of these assumptions, because the first gives you a coarse embedding, okay, outright, and the second one does too, under this weak assumption that E plus E embeds into E. Okay, so in other words, if there's a map with infinite separation ratio, then there's a coarse embedding. So if there's a coarse embedding, there's a map with infinite separation ratio, and vice versa. If there is such a map, well, then there's a coarse embedding. Not necessarily the same map, but another map. Okay. Now, this is about a map that really can separate the things arbitrarily well from each other. So the theorem of today, really the main thing here. Okay, so again, I assume that E plus E is a subspace of E. Then, well, X coarsely embeds into E if and only if. Okay, so from before, if I know that there's a single map with infinite separation ratio, I'm okay. But what if there's not a single map that does it, but rather a sequence of maps that approaches infinity? Okay, so in other words, that's the thing here. I'm looking at the supremum over all functions from X into E, and I take the separation ratios. If this is infinity, okay, so just I can get if I can get arbitrarily large separation ratio, then I can get a coarse embedding. So that's this sort of the main statement. Okay, so let's remember what this means. Okay, so it means that whenever you have a constant k, I will have a map so that I can ensure that things and constants lambda. Well, let's go back to this thing here. Okay, so it means that for all k, I can find a map phi with separation ratio at least k. Okay, so that means that I can find these lambda, etc. Positive, so the delta over lambda is k, at least k. Okay. Things that are within capital lambda of each other, they stay within, the images become less than little lambda, and things that start far apart, they become delta apart, they also get delta apart. Okay, so these different delta and lowercase delta and capital delta. So it's enough that I can find these maps that slowly, okay, separate distances from each other. So essentially, these different, this theorem here and this theorem here, the proofs are very similar. It uses a specific gluing technique I'll just give you a few hints on this. Okay, so maybe I should, what I want to focus on is, well, how on earth is this assumption being used in the proof? Okay. So that's what allows us to do a gluing internally in E rather than construct a space larger than E. Okay, if you, in general, if you have a map from X into E and you try to have a sequence of maps of X into E and you try to glue them together, maybe you're going to jump outside of E. Okay? But this assumption here will allow us to glue things within E. Okay, so what how is E plus E being a subspace of E used? Okay, well, so we get subspaces as follows. Okay, so I start by saying, well, I can get E plus E inside of E. Okay, so that will be my, I'll view that as a direct sum of a copy of E and another copy of E, E1 and E2. And then I'll say, well, E2 is isomorphic to E, so I can split that again, or I can find two copies of E inside of that, and I'll iterate this procedure. So in that way, I'll get a sequence of subspaces of E. Okay, they will all sit inside of a subspace F of E. Okay, so the ENs are all isomorphic to E. There's no uniform bound on the constants of isomorphism. Okay, this just will explode. And I'll get projections. Okay, so these are projections from F onto En. Okay, and again, the constant of projections, or the norm of these projections Pn, will blow up to infinity. I have no control over this, but it will have the property that at least that En is in the kernel of Pn for n and n distinct. So essentially, what I'm getting is some type of decomposition. Okay, F as a direct sum of E1 plus E2 plus E3, etc. Okay, all subspaces that are isomorphic to E. Okay, however, it's not a Schauder decomposition because there's no uniform bound on the projections onto the individual summands. Okay, so that, but that's not really an issue here. Okay, I just have to modify my map appropriately to get this. Okay, so using this, we can construct maps. So from X into the ENs, and let phi be the sum of these phi-ns. Okay, and so then you just have to show that, well, you have to construct these maps in a particular way with particular properties in such a way that the resulting map becomes a coarse embedding. All right. So that's the specific gluing technique here. So let's see what sort of the import of this result. Okay, and I'd like to contrast this with a few other gluing techniques that are around. Okay, so essentially the idea is I have, okay, so for X to embed coarsely into a space E, well, I have to embed an infinite dimensional space. Okay, so a whole space of infinite dimension with two compression modulus and an expansion modulus that both have to go to infinity. Okay, so there are three things. Okay, so to get a simpler criterion, okay, you'd like to reduce it in three different ways. Okay, well, this theorem says, oh, I'm reducing the complexity of that statement by saying I don't need these functional, these expansion modulus and these compression modulus moduli to be to go off to infinity. No, it's enough that I consider. So these will be functions from the reals to the reals. So these are somewhat complicated objects, and they tell you something about the asymptotic behavior. No, I don't need asymptotic behavior at all. I can boil it down to a single distance or a single pair of distances, okay, given by this modulus, or this coefficient, this ratio, the separation ratio. So it's enough that for each number, I can find a map that does things that well. Okay, so that's a reduction in the complexity of the maps themselves. Okay? That's one reduction you could hope for. Another reduction you could hope for is, well, rather than having to embed all of X into E, well, maybe I can just embed balls, larger and larger balls of X into E. So that is obtained in another paper by Florent Baudier and Gilles Lancien, Thomas Schlumprecht, and Pavlos Motakis from a few years ago. So this uses Baudier's barycentric gluing, which is a different techniques, a different set of techniques. So then you have to have it's enough that you embed larger and larger balls of X into E, but on the other hand, the compression modulus and the expansion modulus has to be uniform for all of these maps. And so that's another type of reduction. The third type of reduction you could hope for is, well, rather than restrict sort of the diameter of X, okay, to balls, well, can I reduce it to, can I reduce the dimension? Is it enough to embed finite dimensional subspaces of X into E with some things? Well, that's easy to construct counterexamples to such a thing. The best one can do is you can have some embeddability index, sort of a Bourgain type embeddability index, where you can sort of say, okay, it's a bit more than embedding just finite dimensional subspaces of X, but at least it sort of doesn't require you to embed all of X in all of its infinite dimensions into E. Okay, but then you get an ordinal valued index instead. All right, so that's all I wanted to say.
Okay, thank you very much. Do you have a counterexample to this theorem without the assumption?
No. It's
I think I do.
Okay. This last thing here.
Yeah.
To be honest, I haven't really thought about it. I thought more about.
This is more like looking at sort of equicoarse embeddings versus embeddings. And there's a counterexample. If you take what is called the Jamesification of T star, the dual of Turleson space,
yeah,
then you can equicoarsely embed summing bases, finite pieces, but C0 doesn't coarsely embed into it. And I think that might be the counterexample in this case. And this is a quasi-reflexive space of one dimension, so I think it doesn't satisfy your assumption.
Okay.
Yeah, so it's interesting. So in that sense, it's sort of the best you can do, probably.
I did the best you. Okay. So I should note that okay, the assumption, okay, so what is the assumption that R of phi is equal to 1, okay, if you just want, or at least 1, sorry, this is sort of easily obtained, Okay, if you have if E has an equilateral set, okay, an infinite equilateral set, so all distant, an infinite set, so that all distances between points are the same, and if X is separable, well, then you can always, then it's easy to construct a map from X into E that has this separation ratio at least 1. In fact, it will have separation ratio equal to 1. Okay, so if E doesn't have an equilateral set, okay, but it's infinite dimensional, well, then you can just renorm it and get an equilateral, or get this condition inside. So that's not the difficult. The question is, well, if I can get this greater than 1, does this already imply that the supremum of all, if I have a single map with this thing here, does it imply that the supremum of all maps here is equal to infinity? This I don't know. That might be.
I know. Good.
So
Are there other questions?
you say that might be false.
You mean this last statement you wrote?
Yeah, it sounds like what you are saying could.
Yeah, I hope I understood the definition correctly. But so the situation is the following in this space. Just look at the summing basis. So in this space, you have the summing basis as a spreading model. So for all dimensions, you have the embedding of summing basis. In fact, Lipschitzly. But in terms of if you try to embed the entire summing basis, the C0, you can't do it coarsely. So that's the.
But that's more this this barycentric cluing thing. So I'm requiring for phi be defined on the entire space all the time.
Okay.
Okay, but I'm reducing the complexity of what phi should be. Okay, how much it should separate distances.
I see. It's a little different, but I think probably in that example you can still do it. Okay, so I have to think about it. All right. Are there any other questions and comments?
Yeah. What do you mean? Something I didn't understand. You were talking about embedding into Cyrilson, into what we call T star.
The Jamesification of Cyrilson. So you take you define James space over T star.
Oh, okay.
Yeah, it's not T star.
Oh, okay. Yeah. Oh, of course.
So you get a quasi-reflexive space. Yeah.
Yeah. So yeah, you want something that contradicts the E plus E and E.
Yeah. Yes.
You need that. Okay. Thanks.
Yeah. Yeah.
I mean, it also gives you, okay, so you can ask, yeah, if you have examples where this doesn't hold, okay, where X doesn't coarsely embed into E, then you can ask yourself, well, what is this supremum then? Okay, it's a finite number. In general, will be at least 1. You can prove that number for, if I take L2 and T star, this number is at most 4. That supremum is at most 4. That comes out of.
What is? Oh, you mean embedding L2 into T star? Yeah. Okay. Yes.
You take the supremum between all maps from L2 into T star, and then you get the supremum to be equal to 4. So you know exactly how much you can separate points from L2 inside of T star.
Okay, yeah, but T star is isomorphic to its square.
Yeah, so it satisfies this assumption.
It satisfies it, and yet, I
And
see.
this is
because
what
L2
what I-
doesn't embed. L2 doesn't embed coarsely, right? So that's
Yeah, so I'm saying if I have a space, if my target space satisfies this assumption of E plus E is a subspace of E, okay, then if I know that X doesn't coarsely embed, well, then there's a bound on this supremum. Okay, my conjecture is that that bound should always be 1.
yes, I think I see what you mean. Yeah, that's probably true in that.
Or maybe 2 or something. That should
it's
be
something like it's something like 2 because you can Lipschitz embed it. So it's probably 2, or maybe 2 plus epsilon or something like that. Yeah. So I'm not sure. Okay. Okay. Well, thank you so much for a very nice talk. Last call for questions, or comments. If not, okay. Thank you, Christian. That was very nice.